Now that we have access to the squeeze theorem, it's time to prove a very important limit using said squeeze theorem. And the very important limit that we're going to be proving using the squeeze theorem is going to be the limit as theta approaches 0 of the sine of theta divided by theta. Now, if we were to attempt to make use of the direct substitution property over here, your numerator would be the sine of 0, and your denominator would be 0. And we would see that our direct substitution property has forsaken us. Therefore, we should probably try something else. So what I'm going to do is ask you to recall with me the structure of the unit circle. Now, I do have this very conveniently placed coaster with one of my alma maters, Albion College, featured on it. And we're going to use this to create the unit circle in the first quadrant. So let's see, center of the circle would be right about here. Have that go up. It's a good thing I have the coaster there to make sure that I draw a nice circle for the nice shaky axes that I'm creating here. So when an angle is in standard position, it makes something that looks like this. So this angle, we'll call that theta. The ordered pair that would be associated with this on the unit circle would be the cosine of theta and the sine of theta. Now we could also draw in a reference triangle that comes right down this way, like so, where the horizontal side is the cosine of theta and the vertical side is the sine of theta. Additionally, this right here, this arc that we have here, would have a length that is equal to theta. Now, hopefully it's fairly obvious by looking at this, but I will take the time to explain what's going on as well. The sine of theta is definitely going to be less than or equal to theta. Reason being, if we were to consider the distance from this point to the x-axis, I see two different ways that I could travel there. I could travel at a right angle to the x-axis, which should be the shortest possible distance, or I can follow the arc theta. Now, if the arc theta is, anything but this, it's guaranteed to be longer because we have a right angle here, and that's how you define the shortest distance from a point to a line. So, we definitely have this. Now, given that theta is positive, it'll also be true that the sine of theta divided by theta, if I divide both sides by theta, that's going to be less than or equal to 1. What I'm doing is I'm setting up part of the inequality that we'll be using for the squeeze theorem. Now, additionally, I'm going to draw in one more side here, and that's going to be from this point up to this point right here. The x-coordinate for this point is going to be 1, since that's tangent to the unit circle at the point 1, 0. And as a result, that means that the opposite side over the adjacent side would be the tangent of theta. Now, given that I just described this side over 1, that y-coordinate is going to be the tangent of theta. Now, with that in mind, using a similar argument to what we just did, I am going to show that the tangent of theta is going to be larger than theta. So I'm going to show that the tangent of theta is greater than or equal to theta. The way that I'm going to do so is by adding in one additional side, and that's going to be the line segment that is tangent at our point from the unit circle. I'm going to start labeling points as well because it gets a little bit confusing. This point right here, we'll call this A. Up here, we'll call this B. This point of intersection, we'll call it C. And this point down here that was 1, 0, we'll refer to that as D. Now, if you consider the distance from A to D, you've got the arc, and then you've got these two sides that kind of jut out like this. Now, the shorter of those, based on the picture, is going to be the arc. The arc is going to be shorter than the two collective sides. That's sort of provable using the triangle inequality, but I think more likely you're going to want to take my word for it. So theta is going to be less than or equal to line segment AC plus line segment CD. Now, if you were to compare AC with BC, I do want to point out that at a point of tangency like this would be a right angle, and A, B, and C all form a right triangle. AC is one of the legs, BC is the hypotenuse. So BC is definitely going to be bigger than AC. So this is definitely less than or equal to BC plus CD. Now, BC plus CD is just that line segment, BD. But that line segment BD is also the y-coordinate of the point up here. So put it all together, and we have just shown that theta is less than or equal to the tangent of theta. Now, using some identities and flipping the inequality around, this means that the sine of theta divided by the cosine of theta, that's the tangent of theta, is greater than or equal to theta. I am going to multiply both sides by the cosine of theta and divide both sides by theta. So multiply both sides by the cosine of theta over theta. On the left-hand side, that's going to leave us with the sine of theta divided by theta, and on the right-hand side, we are left with the cosine of theta. So, we now have that the sine of theta divided by theta is less than or equal to 1 from over here, and is greater than or equal to the cosine of theta. I'm running out of room on this page, so I'm going to shorthand the rest of this. I'm going to take the limit as theta goes to 0 of all three parts. What we get in the middle is our desired limit. What we get on the right-hand side is the limit of a constant. That's just going to be whatever the constant is, and that is 1. Limit as theta goes to 0 of the cosine of theta can be evaluated using the direct substitution property. The cosine of theta is going to go to 1. This is already 1. Therefore, we're talking about something that is between 1 and 1. So go ahead, I'm thinking of a number between 1 and 1. What is that number? If you said 2, you're wrong. It is in fact 1. So this super important limit is going to show up a little bit more in the next chapter. Just wanted you to be aware that the squeeze theorem does have some fantastic applications.